Let me welcome you to this lecture. We have been discussing the chemistry of group 12 organelles, and we have so far discussed the synthesis, reactivity as well as structure of organogene compounds. So during this lecture, we will discuss about the chemistry of organomercury compounds. The chemistry or the compounds of organomercury compounds containing organic substituents on mercury are unique, or uh, they differ from the other main group as well as traditional metal organelles in the fact that these compounds, they are inert to the attack of either oxygen or water, which is not the case for other organometallic compounds. Now the reason for this inertness towards water or dioxygen is because this mercury and carbon bond is essentially covalent in nature, because the difference in electronegativity between mercury and carbon is quite less, and that is why the bond is essentially covalent, and this is the reason why these compounds are stable towards reaction with dioxygen or water. Now that is exactly the reason why the chemistry of organomercury compounds thrived in the initial period, because it was easy to handle these compounds, and many of these compounds, especially this phenyl mercury alkoxide, these compounds, uh, OR, these compounds have a lot of medicinal value, as well as, because these were used as fungicides, and also many of these compounds and derivatives found application as bactericide or insecticides as well. So apart from that, organometallic compounds have also been used extensively in organic synthesis, and we will discuss some of the application of these organometallic compounds in organic synthesis during this lecture. So let us begin with the preparation of organometallic compounds. As such, preparation of organometallic compounds, there are several methods. We will discuss some of the most important rules for preparation of organometallic compounds. So one of the most earliest methods for preparation of organometallic compounds essentially starts with an uh, alkyl or aryl halide, and then reaction with elemental mercury in presence of sunlight gives us RAgI. Then one can also start with diazo salts and then do reaction with elemental mercury to obtain uh, organometallic compounds. So diazo salt, diazonium salt, which by the reaction with elemental mercury at low temperature at say 0 degrees Celsius gives us ArAgCl here, and N2 will be a byproduct in this reaction. One can also start with salts of mercury, that is, one can start with AgCl2 say, and then do reaction with organolithium reagents. So RLi will give us RAgCl here, and then subsequent treatment with another equivalent of RLi will give us R2Ag. So there is another very prominent approach for preparation of organomercury compounds. It is known as organomercuration reaction or mercuration reaction. So one can start with Ag 2 plus salts like mercuric acetate, and then do reaction with CH acidic compounds like benzene here, and then this will give us essentially AR, AG, OAC. So this reaction is known as organomercuration reaction. Then These are the most prominent methods for preparation of organometallic compounds. There are some other methods available as well, but we will refrain from discussing all the methods for preparation of these organometallic compounds. We have already discussed that these organometallic compounds, they are inert to a reaction with dioxygen or water, and that is why these compounds are, they are, we can use these compounds in different reactions. But these organomercury compounds, this mercury carbon bond is susceptible to undergo fission or homolytic fission essentially to give us radicals. And this is one of the most important aspect of these organometallic compounds, that they can undergo homolytic fission. That is, either if you heat them or under photolytic radiation, photoirradiation, they will undergo homolytic fission to give us radicals, and mercury will of course come out of these organomercury compounds as elemental mercury here, and will obtain radicals, and these radicals can then be used in different reactions to give us, so for example, it will give, so this will give us substituted aryl compounds, because they and that is why these organomercury compounds serve as good source of radicals. And also this is one of the reasons why organomercury compounds, because they are susceptible to temperature or photoirradiation, they can be used in transmetallation reaction. We have seen already during preparation of, say, beryllium compounds, or during preparation of organozinc compounds, that these organomercury compounds are essentially used as reagents for transmetallation and formation of these organoberyllium or organozinc compounds. And the reason why they can be used for transmetallation reaction is because of the instability or weakness of this mercury carbon bond, which is susceptible to temperature or photoirradiation. Now, if you look at the structure of RAGX or R2AG compounds, that is RAGX, or if you look at the structure of R2AGX, all of these compounds are linear in nature, and they are of course monomeric. But if one tries to do a chemical trick and then make CAGC bonds which are bent in nature, that is, say for example, if we start with this compound and then do reaction with mercury, what we may think is that in this case, this sort of a product is going to be formed where there is going to be bent CHGC bonds. But the reaction does not proceed in this way, because the such organometallic compounds evade bent CHGC bonds, and instead in this reaction an oligomerization is going to occur. That is, it is in presence of potassium acetate, oligomerization is going to occur, and the product with linear CHGC bonds are going to be isolated in this way. So essentially these compounds evade formation of bent carbon-mercury carbon bonds by formation of such oligomers. So another interesting compound, organometallic compounds, are these bis-cyclopentadienyl mercury, and the preparation of this compound one can start with this CP2 TL compounds, which serve as good source of CP ligand and reaction with AgCl2, and this reaction can be of course done in aqueous medium because the product formed is going to be stable even in water, and that is why we can do the reaction in that is C5H5 mercury. So CP2 mercury can be prepared by doing this reaction. And now if you take this compound, it shows very interesting properties in the sense that this compound undergoes diacetyl reaction. So it acts as a diene in diacetyl reaction because it undergoes diacetyl reactions, for example, with maleic anhydride. And also, if you record IR spectrum of this compound, what you will observe is that it shows stretching vibration for mercury carbon sigma bond. So all of these essentially indicate that the structure in this compound, the CP ligand acts as a eta1 ligand, that is, the structure is somewhat like this. So the CP ligand essentially acts as a eta1 ligand. Both the CP ligands acts as eta1 ligand in this CP2 mercury. But if you record the NMR spectra of this compound, what you will find is for such a structure, one should get three different types of protons. That is, the proton that is touched over here is going to give one signal, while these two protons are going to give us one signal, and we will also get another signal for these two protons over here. But if you record the proton NMR spectra of this compound, you will find that there is only one signal in the proton NMR spectra, and that tells that all the hydrogens associated with the CP ligand in this compound are essentially equivalent. And this indicates that there is a fluxional behavior is involved in this particular compound, and that is if you take that is eta1 C5H5 mercury. It undergoes haptotropic shifts, this compound, that is, let us level these carbon atoms 1, 2, 3, 4, 5. Now it undergoes haptotropic shift, that is, this ligand will now become eta2 ligand. So that is going to be negative charge over here, and we'll have this sort of a intermediate, which from where now let us also label the carbon atoms again accordingly. And then now, when eta1 CP ligand is going to be reformed from this intermediate, now the mercury atom can bind to either to carbon C1 or to C2, and that is why we can have eta1. Let's write it this way. So this is center 2 now, This is 1, 3, 4, and 5. So that is how all the carbon atoms are essentially equivalent in this compounds, in this Cp2 mercury compound, because of this haptotropic shift, that is called haptotropic shift. And this sort of haptotropic shift essentially renders or makes all the hydrogen atoms on the Cp ligands also equivalent in the NMR time scale, and that is why we see only one signal in the NMR spectra, proton NMR spectra of this Cp2 mercury, or this sort of fluxional behavior essentially produces only one signal in the Cp2 in the proton NMR spectra of Cp2 mercury. So these are some of the important features of organomercury compounds. We will now discuss the application of organomercury compounds in organic chemistry. So organomercury reaction is a very important reaction and has been known for a very long time. It has many applications in organic synthesis. That is, let us first discuss this organomercury reaction. We have already discussed about the organomercury reaction. That is, one can start with say compounds like aromatic compounds on treatment with mercuric acetate give ARAGOSC, and acetic acid is the byproduct in this reaction. Now, apart from aromatic compounds, also other compounds which have significant CH acidity. Examples of such compounds are, say, for example, acetylene. The protons have considerable CH acidity. Similarly, we can take nitro compounds. Then we also know that this 1,3-diketones like acetyl acetone, also the central carbon atom, the hydrogen atom attached to the central carbon atom, that is at the 2 position, they are quite acidic in nature, and such compounds can also undergo organomercuration reaction. Now, in these organomercuration reaction, it is essentially electrophilic substitution reaction. So one can catalyze this organomercuration reaction by using a strong acid, which is a non-coordinating strong acid. So because it will facilitate the release of acetic acid, say for example here. So if we use say perchloric acid as the catalyst here, so it will facilitate formation of this electrophile, this AgOSC is positive is going to be formed, and then acetic acid is going to be released because it's a strong acid, and that is why it will facilitate formation of the weak acid, acetic acid over here, and this will essentially now go and react on the substrate, this electrophile, so for example in aromatic compounds, and that will essentially lead to the catalyze the organomercuration reaction. These organomercury compounds can also be added to olefins, and this reaction is known as solvomercuration demarcation reaction. So in this reaction, essentially AgX plus is X plus and Y negative. Two fragments are added to an olefin. So we'll see how the reaction proceeds. So let us take an olefin, and now if we add AgX to say, so if in this case X is nitrate or acetate, this sort of anions, and then also add HY. Example of HY could be water or say methanol. So this sort of oxygen containing compounds. Then this will add to the olefin in Markovnikov fashion, and the AgX group will essentially add to the less substituted carbon atom over here, while Y will come and attack on the more substituted carbon atom over here. And now we can do reduction, that is, we can add either NaBH4 or we can also use dihydrogen here, and that will lead to demercuration now. So what we will have is this sort of a product. So because this reaction proceeds to Markovnikov fashion, it complements hydroboration reaction which proceeds in anti-Markovnikov way. So now let us see one example of this solvomercuration demercuration reaction. So if we start with say this olefin over here and then add AgOSC2 in water. So this also PHF is also used in this reaction as a solvent here, and then a mercuration reaction is going to take place, and CH2AgOSC and OH group from water will come and attack on the more substituted carbon atom over here, and then if we now reduce this compound under a basic medium over here, what we will have is the product. This will become CH3 and this is OH. So that is how we see how this solvomercuration demercuration reaction can be used for functionalization of olefins. Another very important organomercury reagent is this Seyfarth reagent, which is phenyl alpha haloalkyl mercury. So this phenyl alpha haloalkyl mercury, it essentially acts as a carbene transfer agent. So example, if we have this is the generic formula. We can also have Seyfarth reagent with two different halogens over here. So we have X and X dash. Now when we do reaction with this safer reagent, it can act as, we have seen that it acts as a carbon transfer agent. That is, these reagents upon heating releases essentially the carbene, that is dihalo-carbene is released. CX2 is going to be released in this case, and in this case as well, the CX2 is going to be released, while the byproduct that is going to be formed is this over here, and in this case, the heavier halide X dash is going to be retained by this mercury, organomercury compound that is formed as a byproduct here, and the lighter halide will essentially be part of the dihalocarbene fragment that is generated in this reaction. So that is how this reagent is very interesting. We have already seen examples of organogen carbenoids, how these organogen carbenoids can be used in organic synthesis. So this safer reagent or this phenyl alpha haloalkyl mercury also complements these organogen carbenoids. The only difference here is that these reactions or these reactions involving this safer reagent can be carried out in much milder reaction conditions, and that is why they are interesting in organic synthesis. So you see examples where this safer reagent is used as a carbon transfer reagent. So if we start with, say, phenyl AgCl and then do reaction with Br in presence of tertiary butoxide, potassium tertiary butoxide as the base over here, this will essentially generate the safer reagent. So that what we will have is phenyl mercury CCl2 Br is going to be generated in this reaction. Apart from that, we will also have KCl is also going to be formed, and then tertiary butanol will also be a byproduct in this reaction. Now you can take this and when we do reaction with an olefin, say, what we will end up with is the carbene is going to attack this olefin, and a cyclopropane derivative is going to be formed in this way. We see that the lighter halide, this chloride, is retained in the carbon fragment, while the heavier halide, bromide, will be part of the organomercury byproduct that is formed, HHCbr, that is formed in this reaction. So another example that we will see that it involves reaction of the safer reagent or carbene formed from a safer reagent with an acetylene. So we can start with this pH Ag X2 Br here. So X is either Cl or Br, and then when we do reaction with an acetylene, say alkyne, then we will produce essentially a cyclopropene derivative here. Sorry, X is going to be retained, and we will have this sort of a product is going to be formed, and then now we can do hydrolysis in this reaction. So the byproduct in this reaction is going to be this one here, and on hydrolysis what we will have is a this sort of a product is going to be formed. So this is how this safer reagent can be used for functionalization of alkynes. So this essentially brings us to the end of this lecture. What we have seen during this lecture is initially we discussed why or how these organomercury compounds are different from other main group organometallics as well as transition metal organometallics, in the sense that they are quite stable to reaction, or they are quite inert to reaction with dioxygen or with water, and this essentially allowed us to exploit the chemistry of organomercury compounds because they can be handled even in presence of air or moisture, which is not possible in case of other organometallic compounds. And this also allowed application of organomercury compounds in organic synthesis. Then we discussed about preparation of organomercury compounds. We have essentially discussed 4 different routes for preparation of organomercury compounds. We have seen that we can start with alkyl or aryl iodides and then do reaction with elemental mercury under in presence of sunlight, and this allows formation of RAGI as the product. Then we have also seen how we can use diazonium salt for preparation of aryl mercury halides, and then we again saw that we can use mercury salts for preparation of organomercury compounds by reaction with either these organolithium reagents or also by reaction of these organomercury salt with compounds having significantly high CH acidity, like aromatic compounds as well as compounds uh, like, say for example, these nitro compounds as well as 1,3-diketones and then acetylines, which have higher CH acidity. Then we discussed about the structure of these organomercury compounds, and we have seen that this mercury carbon bond is essentially susceptible to undergo homolytic fission at higher temperature or under photoirradiation, and this allows one to use these organomercury compounds as source of radicals, and this also allows us to use them as efficient transmetallation reagents so that we can prepare many other main group organometallic compounds starting from organomercury compounds. Then we discussed about the linearity of these organomercury species, and we discussed that RAGX or R2AG, both of these two sort of species, they are linear, so that this carbon mercury carbon bond do not deviate from linearity even when we use systems where one expects to get linear bent C bonds. These compounds essentially evade formation of bent C bonds by oligomerization and thereby forming linear carbon mercury carbon bonds. Thereafter, we discussed about another interesting compound of organomercury compound, that is CP2 organomercury mercury, and we have seen its fluxonal behavior so that it undergoes haplotropic shift, and this essentially allows us essentially makes all the protons in the CP ligands equivalent in the NMR time scale. So when we record NMR, we see only one signal in the proton NMR spectra, but these compounds undergo dial center reaction, and as well as we see mercury carbon sigma bond stretching vibration in the IR spectra, which tells us that the CP ligands in this CP2 mercury compound is essentially uses eta-1 coordination mode. Then we discussed about the application of organomercury compounds in organic synthesis, and we discussed 3 different reactions. That is, the first reaction we discussed is the organomercuration reaction. We have seen how this organomercuric acetate reacts with organic compounds of higher CH acidity to give us organomercury species. Then we discussed how one can use organomercury how one can add this X positive as well as Y negative group to an olefin, and how we can use this reaction as a complement to hydroboration reaction, which proceeds via anti-Markovnikov way, while this A solver-mercuryation demercuration reaction proceeds via Markovnikov in Markovnikov fashion. Finally, we discuss how we can use organomercury reagent like Seyfert reagent as a carbon transfer agent, and how one can prepare cyclopropane or cyclopropene derivative starting from this Seyfert reagent. Another important aspect of this Seyfert reagent is that the heavier halides is essentially transferred to mercury, while the lighter halides are part of the carbene formed during from this Seyfert reagent. So let me conclude this lecture with this, and I thank you very much for being with me during this lecture.